All right, so we're going to go ahead and dip into our last lesson for Unit 4 on reciprocal functions. It's a little bit of a different beast than anything we've been dealing with, but at the same time, it does kind of relate to non-permissible values and paying attention to what causes 0 on the bottom. So first off, let's just review really quickly what a reciprocal number, like what a reciprocal is, So a reciprocal would be simply the fraction flipped, is the way I like to best describe it. So 2/3 reciprocal is 3/2. Okay, so that's what a reciprocal is, if you forget. So then that's why you see I have the function x squared minus 5, and that's assumed to be over 1. If I flip that, you now have 1 over x squared minus 5 is the reciprocal function. Okay, so now we're just going to explore a linear reciprocal function here, in which we're going to kind of see different things that kind of come about because of this graph. Okay, so 1a, consider the function f of x with the equation y equals x plus 3. First of all, a lot of people get confused with function notation. F of x just means function that you're given. So don't be confused by that. And so I want you to do y equals x plus 3, and then we also want to look at 1 over x plus 3. And so that's what this is. Original function, reciprocal function. And so we're going to compare these graphs right next to each other. Okay, I'm going to try to point out a bunch of key points. Okay, so for x plus 3, you can see it's just a nice, straight, continuous line. Okay, we're very familiar with the linear straight line. It's got a y-intercept at 3. It's got an x-intercept at -3. It moves up. The slope is up 1 over 1, and you can see that by the growth here. It's just going up by 1 every point here. Okay, it's a very straightforward line. Now, when we look at the reciprocal function, it's where it gets a little bit different. So you can see that every answer next to, almost every answer next to the original function is just the flipped answer. So -3, -1/3. -2, -1/2. Well, why is it -1 and flipped? Well, because it is actually. -1 over 1 flipped is 1 over -1, which is still -1. So we call those invariant points because no matter which graph they're on, they're going to be the same. Okay, like they share those points. Okay, so you can see I have that situation here and here. Okay, these two spots. Okay, now this is kind of the main thing. I think it's the one thing you really pull away from this section here. The 0, so right here, the x-intercept for the linear line, on the reciprocal, the problem is that gives us 1 over 0. We can't divide by 0. We know this. That's where a non-permissible value comes from. So that creates what we call a vertical asymptote. Okay, as you can see, the graph is forever growing towards that asymptote, but will never hit it. Same thing here. Forever growing, but never hit it. Okay? Because it can't be 3. -3, excuse me. Can't be -3. Okay? That's why it's undefined. And then you can see, here's my other invariant point. And then again, 2 1/2, 3 1/3, 4 1/4, etc. Okay? So that's kind of a good rundown of what's happening with the graph. So we're going to fill out kind of a little bit of the definitions and more concepts right below it that kind of relate to the graph. So we're going to lose this graph for now. So hopefully you have the page, with you or using the book. And you can kind of go from there in terms of linking this stuff together. So here we go. So complete the following statements using the graph above. So the y-intercept of f of x is 3. The x-intercept is -3. The y-intercept of 1 over f of x is the reciprocal of the original, which would be 1/3. And then the vertical asymptote is -3, because that's the line that it could not touch. Okay, then I mentioned, state the coordinates of the 2 points which appear on both the graph of y equals f of x and the graph of y equals 1 of x. 1 and -1. Those were our invariant points. So those happened at, let's be a little more specific. Let's not just say 1 and -1. Let's say the exact points here first. Sorry. Be a little lazy there. So let's say it was -4 was -1 as an invariant point, and -2, 1 was an invariant point. So those are your points that both graphs shared. Okay, horizontal asymptote. Didn't really get a chance to see that in the graph, but I'll just kind of explain. Whenever you have a reciprocal or a fraction, even in general, 1 over something, no matter what, this can never be equivalent to 0. Because any value I put in for x, I can't get a 0 because it's 1 over something. And then somebody says, what if I get 0 on the bottom? Well, 0 on the bottom gets you the non-permissible, and we're in that circle of can't do it again. So your horizontal asymptote is we can't have 0. Asymptote's kind of like what we can't get. Okay, so what happens with that, that's why that graph over here, I'll just draw it really quickly. That's why the graph over here does this. They're growing, they're never crossing the x-axis. So right here you can see it's never going to do it, and it's never going to do it. All the way, infinitely, in both directions. So y equals 0 is the horizontal asymptote. For this lesson and for this unit, we don't hit that really hard. It's more of a calculus concept, but I will just tell you that it is pretty much 0 for this whole section. Okay? When f of x equals 0, the graph of y equals 1 over x has a vertical asymptote. So the 0, that was from earlier, the -3, okay, for the last example, if you want to make a note there, the -3 from our example above was the vertical asymptote. As f of x approaches plus or minus infinity, the graph of y equals 1 over fx approaches closer to the horizontal. So what that's saying is, as that other graph goes forever this direction and this direction, what's this 1 over x approaching? It's approaching the x-axis, which is the horizontal asymptote. Okay, let's get to the next example here. All right, consider the function. Now we're getting to a quadratic one. It gets a little bit crazy here, but try to get through it. So consider the function f of x with the equation y equals x squared minus 4. Write the equation of the reciprocal function. So we'll write that quickly. That's just 1 over x squared minus 4. And write the, excuse me, I already said that. The graph of y equals fx and y equals 1 of x and a partial table of values are shown. Okay, so what they have is, here's what that picture would look like. So just so that you're aware, which is important, the gray line is f of x. The black line is 1 over f of x. And you can see there's 3 pieces of it. Okay? There's 3 pieces because there's 2 asymptotes. So that means there's 3 sections. Let's talk about that first. So let's draw our attention right away to the undefined sections. Okay? We all are familiar, hopefully. X squared minus 4 factored we know is x plus 2, x minus 2. So the zeros are -2 and 2, and that's why -2 and 2 were the problems for our reciprocal function. So we cannot have 2 or -2 in our reciprocal function, which creates our asymptote. You can see it's the zeros of the original. So you draw that dotted line, they're not going to cross, and what I want to point out was, you can see I have 1, 2, I have 3 sections. I have 3 sections, and that's why I have 3 pieces. Okay? All right, good. And then you can see, let's look at invariant points next. I like to look at invariant points and asymptotes first to kind of set my graph up, and then I do my y-intercept. So invariant points, if we go to find that, oh, they're not on here. Okay, but I can find them on the graph. They're always going to be at 1, so you can see at 1 they cross. They're the same spot. If you're over here, they're the same spot. Okay, same thing here. -1, they share. -1, they share. So those points are always going to be the same. That's kind of nice. It gives you landmarks when you're graphing the reciprocal functions without, like right now it's being given to you. When you have to graph without having it, it's nice to have those landmarks. Okay. All right. So we're going to move down here. And again, you can just see the relationships again. 12, 1 12th, 5, 1 5th, -3, -1 3rd, the reciprocal. Okay, the only things you got to watch out for is the undefined, and then also the invariant points in terms of helping you graph it. Okay, so let's move down here and kind of get some of the questions about it going. Okay, I don't want to get off of red, prefer blue here. All right, complete the following statements using the graph and tables of values. The y-intercept of f of x, so what's the y-intercept of f of x? It would be -4. Okay, the x-intercept is 2 and -2. The y-intercept of 1 over f of x is -1/4, conversely. And the equations of vertical asymptotes are 2 and -2. The horizontal asymptote, again, is still 0. Okay, again, that is because, and I'm probably not saying it very well, but no matter what, this equation can never equal 0 for the y. So that creates a horizontal asymptote at 0. Okay, example 1, the previous page, we were able to determine the invariant points of the graphs f of x and 1 over x by using a table of values, y equals plus or minus 1. Explain why we can use the lines y equals plus or minus 1 to find the invariant points of the graph. Okay, and mark these points above. We already marked them, and what they're talking about in terms of lines, and I will go up here and I'll just show you, they're just saying that you can go on your graph and simply just make a line at 1 all the way across, and -1 all the way across, and where that line goes through both graphs at the same point, that's your invariant spots, which is how I visualized it when I put them there for you the first time. Okay. And all it wants you to explain is I mean, you can do it if you want. It's a little redundant. I'm not going to put it on there, but they're saying that it's the reciprocal because 1 over 1 is 1 over 1, and -1 over 1 is -1 over 1 flipped. Okay, and lastly, D here. So the following: when f of x equals 0, the graph of y equals 1 over x has vertical asymptotes. So we know that. The 0 of the original creates asymptotes for the reciprocal. As f of x approaches plus or negative infinity, so this is a review from the previous one, you can kind of tell, the graph of y equals 1 over fx approaches the closer to the horizontal asymptote in the equation y equals 0. Okay, kind of getting our feet wet now. All right, so let's do one. We're going to go through a couple more, just last definitions, and we'll hit some examples here. Okay, so properties of reciprocal transformations. So here we go. When f of x equals 0, the graph of y equals 1 over f of x has a vertical asymptote. Okay. When f of x is positive, 1 over f of x is positive. We notice that. When f of x is negative, then it is also negative. When f of x equals 1, 1 over f of x is also 1. So that's the invariant point. And then same thing for -1. Now here's a tricky one. You might want to look at the picture from before if you'd like. But when f of x increases over an interval, 1 over f of x decreases. Okay, so they kind of flip in terms of increase versus decrease. When f of x decreases over an interval, then it increases. Okay, when f of x approaches 0, 1 over x approaches plus or negative infinity, the graph of 1 over f of x approaches a vertical asymptote, and then the horizontal is this one. Okay. Very good. So let me just go back real quick. I'm going to just show you what it's talking about in terms of increase and decrease. So if you look at this picture here, it's a very good example. Right now, this graph is decreasing. That's decreasing. But right now, right here, this graph, that's increasing. This is increasing. It's from left to right. So from this arrow up, it's increasing. Then here, look what happens. Now it's increasing, decreasing, decreasing from left to right. Okay, and that's what it's talking about. Okay, perfect. All right, suggestions for sketching the graph of reciprocal function. I use this. I go through this. It helps me graph accurately, and it gives you really good landmarks. Zeros of the original function become the vertical asymptotes of the reciprocal. So right away, I put my dotted lines where the zeros are. We learned in factoring and quadratics how to find the zeros like crazy, so we should know that. Mark the invariant points where they share. The y-intercept of the reciprocal graph is the reciprocal of the y-intercept on the original graph. So you can just take the y-intercept and flip it for the reciprocal. Points where y equals 2 on the original graph become 1/2, etc. And then complete the reciprocal graph based on the information above. So right here's kind of 4 main points that you can do to make your graph. All right, let's get to it now. Okay, so the graph of y equals f of x is shown. The x-intercept is 2 and the y-intercept is 3. So they're giving you, so it's a bounced parabola. Okay, let's just different color here so we can see a little better. Okay, so we got a bounce there at 2, and I got that at 3. Okay, so use the suggestions on the previous page to graph this. So let's go through this. And they already have the invariant lines there for me to help me. So this is what I know. First thing I'm going to do, I'm going to draw my asymptote. It does bounce at 2, so that is an asymptote, so it can't be 2. Okay, the next thing I know is that I know that, let's go and do the y-intercept. The y-intercept is 3, so then my y-intercept is going to be 1/3. Okay? The next thing I know is I know that invariant points are going to share. So I know that it's going to share here and share here because that is 1 on the original. And then I also know, since it's a reciprocal, that it's going to have a horizontal asymptote here. So you can kind of see what we have here, and I'll kind of highlight it a little bit obnoxiously, but we have this section and we have this section. So we have 2 sections for my graph. Okay? And so what it's going to do, it's going to make this kind of movement. Go with green, and so it's going to do this, like that, and it's going to do the same move like that. So that is the green is our reciprocal functions graph. Okay, it says B, state the y-intercept of the graph. So we've already done this. We've kind of already answered these. Given that the graph of fx is the equation 3/4 x minus 2 squared, state the equation of 1 over. So it would just be the same thing but over. So we flip the 4/3, and you put the x minus 2 squared on bottom. Okay. And D, use the graph calculator to verify. So go ahead and look at your calculator if you'd like. I'll pause the video for a second. All right, so I hope you got that taken care of in terms of verifying your graphing calculator. All right, so now, we're on example 2. The graph of the quadratic function fx is shown. The x-intercepts of the graph are integers, and the maximum value is 2. Okay, sketch the graph of y equals 1 over fx. So we're going to use information that we see here. So things I'm going to look at, the things that are important, okay, in terms of using for help. That's important. That's important. Those are asymptotes. Okay, I also can draw my y equals 1 line, or y equals negative 1 line. So I'm going to have 4 invariant points where those intersect. So first off, I'm going to draw my asymptotes. So let's do that. Right through the 0. Right through the 0. Okay, then here's my invariant points. Whoa, that's wrong. Right there. Sorry, I was a little bit to the left. Right there, and right there. And we can see that we have, again, like I told you before, we have 1, 2, 3 sections here because we have 2 asymptotes. It creates 3 sections. We're going to have 3 pieces of our graph. We still need to understand that we're still going to have the horizontal asymptote, and that kind of boxes things down. So what kind of happens that I feel is very helpful is that I know I have a point here, and I know I can't go above this red line or past the asymptote. So it kind of boxes you in that this is all it can do. Okay, it's the same thing on the other side. They're usually typically mirrored there. Okay, the last thing I'm going to look at is I have the top piece here. Well, they said the max is 2, so I know 1/2 is going to be right about here, right below it. That's a little bit too low for 1/2. Let's move that up a little bit. Okay, so right about there. And then you can see this is going to go up through the invariant points this way. That's the only thing it could do. Okay, and so right there is the green is your reciprocal function. Okay, so state the equation of the asymptotes of the graph. It was x equals negative 2 and 1 was the equations for the asymptotes of the graph. The point a 1/2 lies in the graph of 1 over f of x. State the value of a. It looks like a was negative 1/2, but the way you can do that is you can solve. So it's going to be this right here is that it's asking where is this, and so it's essentially it's at negative 1/2. In just 1 second here. Okay, sorry. So what they did to figure that out was that if negative 2 is right here and 1 is right here, the vertex has to be halfway between. So I just know I have to go negative 2 plus 1 divided by 2 is negative 1/2. So that's where I kind of conclude what we're working with there in terms of the A value they're asking for in C. All right. Okay, we got one more example, and that's it. All right, kind of like this one. Kind of makes you think backwards. Okay, so this graph, g of x is 1 of f. So they're giving you the reciprocal function. So this is the reciprocal function. So a couple things we can see is that it is not crossing here, so you can see that's the horizontal. There is no vertical asymptote. That's interesting. So that means there's no 0. So then we have to go back and think, okay, what does that mean? Well, that means it's going to be a parabola that's doing something like this. It didn't cross. Because all linear lines are going to cross. So it's not linear. It has to be a parabola, and you can kind of see the parabola look to it. So it says this to me, though. The maximum point of g of x is -3, 2. So it says right here is -3, 2. Okay. And then it says the y-intercept of g of x is 1/5. The y-intercept, so right here is 1/5. Okay. And so what we need to do is kind of work backwards. What's 1/5 flipped? 5. So we know our parabola that we're going to have is going through 5. Okay, what's what's 2 flipped? 1/2. So we know we're going to be at right there. Okay, we're going to be at -3, 1/2 for my original. And the last thing we want to go ahead and steal is the invariant points. So right there, we have enough that we need now. Right through there, boom. Right through there, boom. There's my parabola that came from the reciprocal function. Okay, it says that given the f of x is a quadratic function, sketch the graph of y equals fx on the grid and state the coordinates of the minimum point. Okay, so we already have it sketched. The minimum point is going to be -3, 1/2 is the vertex of our original. The minimum point is 1/2. Okay, b, f of x can be written in the form of a times x minus p squared plus q. Determine the value of a, p, and q. Okay, we can do that quickly. So this is off from our unit 3. So let's go ahead and set up everything that we have. Let's do, so we have x minus p. So minus p would be +3, opposite of the x there, which is -3, squared plus q in this case is 1/2. So what we're going to do is we're going to steal a point, any point on our parabola we have, which I'm going to go take the easy one. I'm going to take 0, 5, and I'm going to plug that in for x and y, and I can solve for a. So I'm going to put 5 in for y. We don't know a. We're going to put 0 in for x, +3 squared plus 1/2. Okay, so then I'm going to keep solving here. 5 equals, that's going to be 9a plus 1/2 minus 1/2. So 5 minus 1/2 is 4.5, or you can write 9/2 if you want, equals 9a. My a's and 9 look too close, don't they? 9a, and we're going to divide by 9, and 4.5 over 9 is a nice even 1/2. So a is 1/2, so we are done. So our equation in standard form of the parabola we created is 1/2 x plus 3 squared plus 1/2. Okay, and that is all for our last lesson for unit 4.